Hi, my name is Sean Handler. I'm a Principal Solutions Architect with AWS, and I focus on our search services, including Amazon Elasticsearch service. I'm really excited to be here today to talk to you about what's new in the service. We're going to do a little bit of a deep dive, cover some best practices, and get right into the material. The majority of our customers use Amazon Elasticsearch service for log analytics. In log analytics, we have a challenge where your data is distributed and very fine-grained, and you need a better picture of that data. You use Amazon Elasticsearch service by flowing that log data into the service and then using the bundled Kibana for visualizations and dashboarding on top of that data. Amazon Elasticsearch service is a fully managed service that makes it easy to deploy, manage, scale, and secure Elasticsearch in the AWS cloud. A number of different service benefits, just a light brush really. We have a fully managed service, again, that makes it easy to deploy Elasticsearch in the AWS cloud. We provide the usual APIs, so we're API compatible with an open source version of Elasticsearch self-managed installation. We provide knobs and levers that make it easy to make your Amazon Elasticsearch service deployment cost effective. A number of different security features that bring the ability to do fine-grained access control and hit compliance regimens and all of that. We bring high availability features, make it scalable, easy for you to get deployed in a stable, durable manner. And we have integrations with other AWS services that make it easier to get data into Amazon Elasticsearch service. We can do a quick comparison between a self-managed and an Amazon Elasticsearch service deployment. You can see on the left we have a number of different jobs and tasks that you perform if you're self-managing. If you're using EC2, some of that work is done by EC2. And then finally, if you use this Amazon Elasticsearch service, we take care of a large stack of tasks for you, leaving you free to focus on your application development and your usage of Elasticsearch as opposed to managing the cluster itself. Just a quick couple of examples. We have two main workloads. I mentioned log analytics, that is, are larger by volume. Search is really the core workload for Elasticsearch. Elasticsearch enables you to send your application data in and provide relevant search results for your end users. Compass is an example of a real estate company that enables you to find housing across real estate data. Very typical search workload on the service with that. For log analytics, we have, again, that's our majority workload. We do have a number of different customers, Autodesk being one of them. They have a centralized logging environment that they use to manage their infrastructure and monitor what's going on in near real time. We're going to move into a little bit of a deep dive into Elasticsearch and Amazon Elasticsearch service, just to give you a feel for how the service works. Elasticsearch is a database technology. It's in the database world. And the interaction pattern for Elasticsearch is very familiar if you're familiar with databases. So in particular, we have our two workloads on the left here. There is the logging workload, where you have your server, your application, your IoT, etc. logs. And we have the search workload, where your application data is very frequently stored in a relational system or is stored in a NoSQL system. You're going to send all of that data to Elasticsearch via Elasticsearch's REST APIs for indexing and querying. Elasticsearch then will index that data and will make it available for searching and analysis for log data. One differentiator for Elasticsearch is that Elasticsearch indexes every field. So all of the JSON that you send in, you're going to be able to search against the keys, the JSON keys in that JSON. And then on the output side, your analysts, your application, what have you, are going to send queries to Elasticsearch via REST API, and Elasticsearch will respond with query responses that are either relevant result sets or are analysis kind of results. When you work with Elasticsearch, you send your data in, and then Elasticsearch is going to create an index for that data. Index is a little bit like a database table. Your index is going to organize all of the information that enables searching against it, much like, again, a table in a database. The best practice in terms of lifecycle is to use a rolling index pattern that is bounded either by time or size. Time is our most particular bound, so usually you'll see an index per day is a very common strategy. When you manage the lifecycle, then you're going to do that index per day. Kibana is able to search across all of those indexes to provide the visualizations and dashboards just based on a time slice that you're going to set in Kibana. But the index itself is the underlying organization of the data and how you manage the lifecycle in your domain. At the end of the lifecycle, you're going to just delete your index, much like dropping a table in a database. This is the performant way to move data out of the domain. Now, indexes, if we peel back the layer peel back a little bit more, an index is comprised of a set of shards. The shards are the partitioning of your data within that index. The shard is the sort of core actor in Elasticsearch. You can think of it as such. And you're going to set a primary shard count when you create that index. If I set a primary shard count of 5, then a fifth of the data will go into each of those 5 primary shards. Elasticsearch also enables you to set a replica. A replica is a full copy of the set of primary shards. In this case, I have 5 primary shards and 1 replica, which is another 5 shards. Elasticsearch then distributes the shards themselves across nodes in a cluster. So Elasticsearch is a distributed database, and you're going to provide, for the service, you're going to provide a set of instances that you want to use to serve as data nodes, and that is how you put resources against your workload. When your queries and your updates come in, they'll be distributed across the data nodes in the cluster, and the data nodes themselves have CPU resources. Your Elasticsearch threads are going to pick up the requests and process them based on which shard they're accessing. Now, we have this whole clustered solution, and we've been talking about data nodes, but actually we have a tiered set of data nodes. With our release of UltraWarm in preview last reInvent and general availability this last May, you can now use UltraWarm to tier your storage out. When you use UltraWarm with Amazon Elasticsearch Service, you first index your data into a hot tier. The hot tier is simply a set of data nodes that is going to do the indexing and is going to provide you the best latency to view that data. Then, as you're under operation, you will move your index from your hot tier to the UltraWarm tier. The UltraWarm tier is designed to provide cost benefits through storing data in S3 and then caching that data locally to give better performance, but ultimately you're going to be saving on cost because the data is going to be stored out in S3. When we do this migration, then we have some work that we do to optimize that index for its storage in S3. In particular, we're going to merge down that index. We're going to drop replica shards. The replicas initially are for redundancy. When you use UltraWarm, because they're stored in S3, that data redundancy becomes less important. We have durability for the data in the S3 layer. And then finally, we're going to snapshot through the index migration and make that data available in S3. When you use UltraWarm, it's transparent to you. So you don't have to worry about which storage tier is holding the index. If we look here at our domain, and this is our cluster, we have a set of leader nodes, and then we have our hot tier with our indexing and near real-time performance, and we have our UltraWarm tier that's going to deliver lower cost but higher latency for your request. So the leader nodes are going to maintain the cluster state and keep that cluster as a cluster. The data nodes are our indexing and analysis for the data. They use instance storage, whether it's on instance or network attached via EBS. And we have our UltraWarm nodes for lower cost storage of longer term data. And Elasticsearch, again, is going to route those requests seamlessly. So you're not going to have to worry about where the request is going. You simply send your request. Elasticsearch will handle it normally. I wanted to give you a quick pointer to a little bit of sizing information. This is a very large topic. But again, we're building a cluster here of instances, and the resources that you have available in the cluster are tied to the instance types that you pick. And it can be a little bit confusing at first to try to figure out what are the right instances. I do have a blog post that I've referenced here, and you can follow that QR code to get to that blog post. But just in brief and in abstract, we generally look at a couple of different steps in sizing. The first of those is to examine the storage. Storage is pretty straightforward. You can go from your source data size to an on-disk size with a fairly simple formula that is directionally usually quite right. So I've said approximately 2.2 to 2.5 times the size of your source data is the amount of storage that you need. This is because, again, the replica is going to double it, and then we have the index size is going to be slightly larger from inflation, and then we also need to deploy overhead. So this can give you a baseline, and especially for a log analytics workload, by the time you have the storage amount that you need deployed, you often have enough CPU. But as we dig into sizing, we also want to look at the CPU, and you should evaluate how many shards are actually going to be receiving requests. If I think about a log analytics workload, I have my rolling index pattern. Each index is comprised of a set of shards, and those shards are active based on how I'm writing the data, right? Today's index is going to have active shards. Yesterday's index is far less likely to have active shards, or if they are active, they'll have low activity. So ultimately, what we want to do is put CPUs against shards to ensure that we have enough processor capacity to handle the workload. Our general best practice guideline is to use 1.5 vCPUs per shard in the instances as you deploy them. We have a number of different instance types that we support, and R5 and i3 are really our best performers for high capacity, high volume production workloads. So look at those first. C5s are often relevant for a search workload, which tends to really need more processor than it does storage. Putting Amazon Elasticsearch Service into context, for a search workload, you typically will have your, well, I've put a 3-layer architecture here, a little bit of a straw man to just understand how Amazon Elasticsearch Service fits into the overall picture. So we have our presentation layer. There's going to be some kind of CloudFront or other distribution layer, maybe a little logic there in terms of page rendering. You also have the business layer where you have some business logic. And then you have your database layer where you're storing the data for your application. You will typically see you'll typically use a relational database like one of the RDS, MySQL or Oracle or one of those as your main catalog, your source of truth. You also will quite frequently have some NoSQL store that is managing the higher velocity, more near real-time data, things like inventory and clicks and user ratings, things like that. And then you have Amazon Elasticsearch Service to provide the search on top of your catalog. And it's very common, you're going to flow your data from your catalog, you're going to pick up any high velocity information, you're going to add that to the JSON as the documents as you're sending them into Elasticsearch. And then Elasticsearch really here is a destination. It's not really a source for data. It's a way for you to provide search to your end user. So Amazon Elasticsearch Service is going to provide the search experience, and then you're going to show the data or bring that data from the main catalog for display to the end user. Looking at Amazon Elasticsearch Service in a log analytics workload, there are several phases or steps that we typically go through, And there are many, many different architectures that can implement these steps. We'll look at the common pieces, and I'll give you some examples of the kinds of solutions that you can use there, the kind of tools that you can use in each of those steps. So number one, we have a set of producers. These are application instances, maybe they're IoT devices, maybe they're AWS services. In some way, we have a set of services that are generating log data. We need a collection layer that is going to bring all of that data forward. Typically for an application, you will have on the application server some collector that's forwarding data. We have some examples here from AWS services, either Amazon Kinesis agent or the CloudWatch agent can sit on your application servers. We also have Elastic's beats. These are lightweight log shippers. Fluentd and FluentBit, especially around containers, are very common choices to collect the log data. You then need some kind of aggregation layer. You can actually send the data directly from the collector to Amazon Elasticsearch service. However, in order to avoid overloading Amazon Elasticsearch service with concurrency, you really need a layer that's going to bring, especially at scale, you need a layer that's going to bring all that data together and reduce the number of concurrent connections by building bigger batches out of that data. We have some examples here. We have Kinesis Data Firehose can deliver directly to Amazon Elasticsearch service. We have managed streaming for Kafka. Kafka is a very common tool that's used whether it's the managed service or whether it's a self-managed Kafka. That's a common way to bring data forward. We often use S3 as a kind of queue, if you will. So the collectors can push data to an S3 bucket, and then you can pick it up from there with, for instance, Logstash. Logstash is an open source tool that is a streaming ETL on top of log data. So Logstash is a very common component in this tool chain. The one other thing that you need to accomplish in the aggregation layer is to transform the data. When it's sitting on the application server, it's a text file with line-by-line log lines. So as it's coming through the pipe, and typically in this aggregation layer, you'll transform that data into JSON, which is the format that Amazon Elasticsearch service needs. The aggregation layer is then going to deliver the log data to Amazon Elasticsearch service, and then you'll use Kibana to visualize and dashboard against that data. I wanted to also cover security in some depth. I do have an online tech talk covering our security features, and we have some exciting developments, some new stuff that we brought out there as well. We'll cover that here. Amazon Elasticsearch service has a multi-layer security model. There are a lot of different points that you can intervene to secure requests and to secure your data to make sure that only the right people are accessing them. At the top layer, you can enforce TLS, transit layer security, so that traffic is encrypted as it comes to your domain. We have a number of different login experiences if you're using Kibana. So we support integration with Cognito. Cognito will generate for you a login screen. You can use a username password based on your Cognito identity and user pools, and then that would back out into an IAM role. We've recently released native integration with SAML providers, and so this enables you to use your SAML provider to create a login experience and generate credentials and authentication authorization information against your SAML users natively. Finally, we have our Open Distro for Elasticsearch security plugin. This is going to provide you with a login experience that's a username password that you manage within Amazon Elasticsearch service. If you're using direct to API and you're using AWS SigV4 signing, that would also back into an IAM user or role. Or if you're using Cognito, that would back into an IAM user or role. Your domain can have an IAM policy attached to it, and that policy enables you to restrict access at a fairly coarse-grained level based on that IAM identity. If not, you're going to pass that traffic through, and the authentication and access control will be handled further on in the chain. We support domains with endpoints that are on the public internet. Our best practice, though, is to deploy your domain into your VPC. With VPC, you're able to use security groups to gate the traffic and to make sure only authorized traffic can actually reach your domain's endpoints. As we get to the finest grained access control, we have our Open Distro for Elasticsearch security plugin. This supports role-based access control for all of the identities that we've been speaking of, and enables you to differentially access all of the data in the cluster based on a role that you define within the Open Distro plugin. Within the cluster itself, we support enabling TLS node-to-node communication. With that, you have encryption to the endpoint and then encryption all the way across the request processing. At the deepest layer, the storage layer, we support integration with Amazon KMS. This enables you to encrypt your data at rest, both on the disks and in UltraWarm and in your snapshots. With all of this, you're able to create a secure environment where you can, at a fine-grained level, gate access to the data in your Amazon Elasticsearch service domain. We have a workshop that goes through a full architecture that provides a search experience as well as a back-end logging setup, and that allows you to work with the security model within Amazon Elasticsearch service. I put a link to that here as a QR code. Feel free to go and run that lab. It really is a great lab. It covers both search and log analytics experience. As you own and operate Amazon Elasticsearch service, it's important to take advantage of a couple of features in the service that give you better reliability, stability, and durability. The first of those is to employ dedicated leader nodes. Leader nodes orchestrate the cluster, they hold the cluster state, they maintain the cluster status as a cluster. Every Amazon Elasticsearch service domain, every Elasticsearch cluster has a leader node. That leader is elected based on the eligible nodes. The problem is, if you don't use dedicated leader nodes, then the data nodes themselves will be elected as leader. Those data nodes get loaded, and if they become overloaded with requests, then they no longer can perform the leader function. Employing dedicated leader nodes enables much more stability in your cluster because that leader function then is handled by a single instance. And you're going to want to use that whether you're using single or multi-zone. If you're using more than one, we're always going to deploy the leader nodes across 3 zones when available in the region. Now, we mentioned multi-zone there. We have a one-click deploy across multiple zones. With this, we'll split your data nodes in your cluster across the zones that you deploy, and we'll split your data so that it is replicated and 100% of your data will be in each of the zones. You can choose 2 or 3 zones. Best practice here is to use 3 zones to make sure you get your data split as far and wide as possible. I do have a quick best practices checklist that we can run through. Number 1 best practice: deploy, monitor, adjust. Elasticsearch is a complicated technology, and getting it dialed in for your workload is a process of estimating your deployment, deploying it, monitoring it, and then adjusting it. That's our number 1 best practice, is to expect that you need to do a little bit of tuning on your cluster, and you need to sort of stay on top of the cluster metrics so that you can adjust it. Use the bulk API. We talked about this a little bit in the log analytics example. You can send single documents. However, you then incur the overhead of the connection and all the networking for each document. Use the bulk API. That enables you to send batches. That reduces the overhead greatly and gives you a lot more capacity. Always use 3 dedicated leader nodes. We talked about how dedicated leader nodes give you additional stability. Important that you use them. Select 3 zones when you use multi-AZ. Even if you only have 1 primary and 1 replica, we still split data, and it still gives you the best coverage in terms of zone availability. Elasticsearch has a template feature that enables you to apply settings to indexes when they are created. I encourage you to go look at this. Templates are the best way to do lifecycle management or to do index creation during log analytics workloads. We want to make sure that you maintain free storage. We always want to maintain at least 15%. So we recommend that you set an alarm at 25% free storage space. In other words, 75% used. And then have a look at your cluster and your growth in data to make sure that you have enough overhead. We mentioned the shard to CPU ratio. You want to make sure that you have enough compute capacity to handle the workload. You do that by setting your shard to vCPU ratio initially at 1 shard per 1.5 vCPUs. And again, this is active shards. You're going to have passive data in your longer tail logs that is not considered active, and you don't need to include it in this ratio. For log analytics, you want to set a shard count so that your shard size is approximately 50 gigs. For search, we tend to do more work per shard, and so you want to have smaller shards. We say 30 gigabytes is a rough target for search. Search is much more variable. It's much harder to give a general guideline. You want to set your number of shards and your number of nodes so that you don't overwhelm your Java heap with just the static data you need to maintain shards. We say set the maximum number of shards per node that we would support is 25 per gigabyte of Java heap. We use half the RAM for the heap, so if you're on, say, a 64 gigabyte RAM instance, that would be a 32 gig heap. We do cap at 32 gigs. That would support up to 800 shards, passive and active, for that node. Finally, you want to keep your total shard count less than 30,000. The total set of shards in the cluster is going to really impact the leader node in terms of the processing that it's doing in tracking what's going on in the cluster. 30,000 is really a top end of what we'd like to see in any cluster, because the leader is then going to become a bottleneck. I wanted to spend a couple of minutes just talking about some of what we've been up to over the last 18 months. One of the big things that we've been up to is we launched an open source project along with a couple of other supporters called Open Distro for Elasticsearch. This provides a fully Apache licensed version of Elasticsearch open source along with plugins that we've been developing in open source. You can see some of the plugins that we've developed, and we've been moving those plugins into Amazon Elasticsearch Service to provide additional features and functionality. We encourage everybody to be involved. I put a link to the project page as a QR code you can see there. Follow that, participate on our forums, contribute bug reports, contribute code if you like, and eventually much of that is moving into the service. We have a number of features, and you can see our pace of innovation has been quite rapid. If we look at our version currency and overall currency, number of different launches, we roughly have launched support for an Elasticsearch version per quarter. We've increased our limits in terms of domain sizes. We've made it easier to deploy newer instance types. We brought out changes that keep the service current. In the ease of use bucket, we have a number of different features that we've come out with to make it easier to use. We're going to examine some of those in a second. And then in the security world, we've again come out with SAML most recently, but we have a number of different features there that make it easier to secure your domain. We have covered UltraWarm in some depth, but just to draw the point, UltraWarm enables you to store more log data, to retain that data for longer term analysis. We can see cost reduction of up to 90% versus storing that data in the hot tier. We've also designed UltraWarm to deliver better performance than a usual hot, warm, cold architecture, which is typically based on high density storage nodes that have lower compute. So with UltraWarm, we deliver up to twice the performance of those more dense storage nodes. Index state management enables you to automate the lifecycle management of the data in your Amazon Elasticsearch Service domain. You write a little JSON document that is basically a finite state automaton that moves your data through the various states in its lifecycle. So again, you're sending data into Amazon Elasticsearch Service. It will be indexed on your hot tier. In your ISM policy, you'll specify that you're going to move that data to UltraWarm at a certain time interval, usually 7 days or so. You retain it in there for usually something like 30, 60, 90 days, and then your policy specifies that that data should be deleted at the end of that time frame. We've also come with cross-cluster search. Cross-cluster search enables you to connect to Amazon Elasticsearch service domains so that you can just federate queries across multiple domains. This is especially useful in multi-tenant situations where you can decompose into single tenants and scale independently. As well, it's useful for very large-scale workloads where you need to decompose in order to maintain reasonable size clusters, but you can still search across them with cross-cluster search. We also have most recently come out with custom domain names and integration with SAML providers. We've spoken a little bit about SAML. For custom domain names, you set up a domain, DNS domain with your DNS provider. You then use the Amazon Certificate Authority to bring in your certificates and then publish those to the domain so that you can use that custom endpoint for Amazon Elasticsearch service domains. On the SAML side, again, you're going to create your SAML application. It's going to be, we support things like Auth0 and Okta and Ping, common SAML providers, that you then bring the metadata into the service, and when requests come in, they are authenticated. For Kibana, they're authenticated via the application, the SAML application, and then you can do the fine-grained access control based on the Open Distro for Elasticsearch security plugin. KNN search enables you to bring in machine-learned vector data and use that vector data as the basis for matching queries that are coming in against that data. One usual use case here would be image matching, where you learn a multi-dimensional vector of features in the images. You search based on a multi-dimensional vector of the target. And with KNN, you can find nearest neighbors in the multi-dimensional vector space as a matching portion of your algorithm. We've also come with streaming anomaly detection. Streaming anomaly detection enable Elasticsearch on a particular field, Amazon Elasticsearch service on a field, and then Amazon ES will learn the typical values in that field. If that field value should go out of range, then the streaming anomaly detection will generate an alert and can bring you that alert when you go out of range. So this is typically used in a monitoring situation where, say, CPUs should remain within a particular band. If they go out of band, then something maybe is going wrong. We also have a Learn to Rank plugin that we've launched. With Learn to Rank, you are able to take the results of your users interacting with your search results and learn how better to rank your data. This involves a machine learning system that's going to take the output in terms of your search results, a training set, some judgments, pre-built judgments about that data, and then feed all of that into Amazon Elasticsearch service, where we have our Learn to Rank plugin. Learn to Rank plugin will re-rank output based on how users have interacted with the data before. Finally, we have some advanced querying features. We are working on a SQL workbench in our Open Distro project. This will make it easier to use SQL against Amazon Elasticsearch service. Also, we have pipe processing language. This is going to enable a more Unix-like flow of sending a query, taking the output of the query, the results of the query, feeding them to a chain of processors that enable you to build complex results and reporting based on that. Thank you very much for your time and attention. Really excited and hope you get out there and do stuff. Let us know.